Hey guys, if you remember last time, we kind of talked about the basics of the polar coordinate system, and so we graphed some points. We talked about how to convert some equations from rectangular to polar coordinates. So if you remember, we talked about graphing things of the form r comma theta. So those are what the points in the polar coordinate system look like. And so what we're going to talk about now is how to graph equations in the polar coordinate system. So in the rectangular coordinate system, you usually see functions that are some function of x, and we usually write that as y equal to f of x. Well, in the polar coordinate system, it's similar but a little different. So in the polar coordinate system, we usually call our equations r, and they're written in terms of theta. So the way that we say that is r is equal to f of theta. And so the graph of a polar equation consists of all points P that have at least one polar representation, r comma theta, because that's how we write our points, whose coordinates satisfy the equation. So that's a big long definition, and basically all it means is we're going to plug in values of theta and get out values of r. And so the reason we do this is, like I said in the last video, that many equations are more easily represented in the polar coordinate system than they are in the rectangular coordinate system. And we're about to look at a few examples. Okay, so now let's look at a few examples. The easiest way to graph equations in the polar coordinate system is simply to make a table of values, just like you did whenever you were first learning this in algebra and you were graphing graphs on the xy plane. So instead of x and y, we're just going to be plugging in values of theta and getting out values of r. So for the first example, let's sketch a graph of r equal to 2. And I think we looked at a few of these examples in the last video, but we kind of just thought about them a little less algebraically and a little more geometrically. And we also want to express the equation in rectangular form. So if we think about what it means for r to be equal to 2, let's make a table of values. So we have r and we have theta. And our table of values is going to look like this. We can pick any theta we want. So usually it's easy to pick your multiples of pi over 2, unless you have an equation where some other multiple works better. So we're going to start with 0, pi over 2, pi, 3 pi over 2, and 2 pi. And for this equation, since r is equal to 2, we know that every value in the r column must be equal to 2. And so this gives us 5 points that we can start with when we're graphing our equation. So first, let's graph the point 2, 0. So we go out to the circle of radius 2, and we don't go around at all, because theta is equal to 0. For the second point, we go out to the circle of radius 2 and around to the angle pi over 2. For the third point, out to the circle of radius 2, around to the angle pi. And the fourth point, we go out to the circle of radius 2 and all the way around to 3 pi over 2. And notice if we were to graph that fifth point, it would fall right where our first point was, so we're done. So once your graph starts to repeat itself, that's how you know that you're done, and that will happen on a lot of these polar graphs. So now you can kind of see that this general shape is a circle of radius 2. And you would see that better if you were to fill in other points, but we're just going to stick with these 5 for now. So that is the graph of r equal to 2. So now what we want to do is express the equation in rectangular form. So if you remember, the general equation for a circle was r squared is equal to x minus h squared plus y minus k squared. And that comes back from college algebra. So all we have to do now is plug in the center of our circle into the letters h and k and the radius of the circle in for r. So the center of this circle is at 0, 0. It's at the origin. So what happens on the right side is we get x minus 0 quantity squared plus y minus 0 quantity squared. And that is going to be equal to our radius, which is 2, and we want to square that. So the final equation of our circle is just going to be 4 is equal to x squared plus y squared. And so that is our rectangular coordinate equation. All right, let's look at another example. I think we did this one too in the last video. So the next one, we want to sketch the graph of theta is equal to pi over 3. And again, we want to express the equation in rectangular form. So let's make our table of values. So we have r, we have theta. And this time, we can't really pick a theta because we know that no matter what we pick, we're going to get pi over 3. So let's go ahead and write some pi over 3's in there. So this time, it's probably a better idea to pick values of r. And it doesn't matter what you pick, so let's just pick a couple of negative ones maybe, and a couple of positive ones. So I picked -2, -1, 3, and 4. And so now, just like in the last problem, we have to go through and graph our points. So let's first graph the point -2. So instead of going to the right this time, we go to the left out to the circle of radius 2, and we rotate through an angle of pi over 3. So that would be at the 240 degrees over there. Our next point is -1, comma pi over 3. So we go out to the circle of radius 1 to the left and around to the angle pi over 3. And for the point 3, comma pi over 3, we go to the right this time since we have a positive radius, out to the circle of radius 3 and around to the angle pi over 3. And finally, for the point 4, comma pi over 3, we go out to the circle of radius 4 and around to the angle pi over 3. So if you notice, these lines are making a straight line with a slope that is at the angle of pi over 3. But we can't say that pi over 3 is a slope because pi over 3 is an angle. So we need to figure out what that translates to in the rectangular coordinate system. So if you remember from algebra, any straight line can be written in the form y equals mx plus b, where m is the slope and b is the y-intercept. Now in the case of our equation here, our line goes through the origin, so b is going to be 0. So what we're concerned about is finding that m, or that slope. So if you think about your trig functions, the one function that comes to mind when you think about slope is tangent. So remember this equation from the last video, we have tangent theta is equal to y over x. So if you think about the slope equation, slope is basically rise over run, or you can kind of think about this as y over x. So it's some change in y over some change in x. And that's why the tangent function is a good way to find a slope. So in this case, we just have that we have the tangent of pi over 3, and that's going to be equal to our slope. So we first need to think about what is the tangent of pi over 3. Well, if you think about tangent, we know that tangent of pi over 3 is going to be equal to the sine of pi over 3 over the cosine of pi over 3. And so that comes out to be square root of 3 over 2 times 2 over 1. And if we do that division or multiplication, however you want to look at it, we get that the tangent of pi over 3 is the square root of 3. So that is the slope of our line. So we can rewrite this equation of a line as y is equal to the square root of 3 times x. And that is the rectangular equation for the polar equation theta is equal to pi over 3. All right, we have one more example with this. So we're going to sketch a graph of r equals 2 times the sine of theta, And again, we want to express the equation in rectangular form. So let's start with a table of values. So again, we have r and theta. And this time I think it's better off picking values of theta. So let's just start with, let's do 0. Let's do pi over 6 this time just to see what happens. Let's do pi over 2, 5 pi over 6, and pi. Okay, let's make our table of values this way this time. We have theta. Let's do r on this side since we're actually going to be calculating r. So for the first one, we have 2 times the sine of 0, which is 2 times 0, which is 0. So our first point is going to be 0, 0, and that would be right there. Our next one, we have 2 times the sine of pi over 6, and so that would be 2 times 1/2, which is 1. So we go out to the circle of radius 1 and up to the angle pi over 6. Our next angle is pi over 2, so we have 2 times the sine of pi over 2, and that is equal to 2 times 1, which gives us 2. So now you might be seeing why I picked those weird pi over 6 angles in there. So we go out to the circle of radius 2 and up to the angle pi over 2. We have 5 pi over 6 next, so we have 2 times the sine of 5 pi over 6, which again is 2 times 1/2, which is just 1. So we go out to the circle of radius 1 and around to 5 pi over 6. And if we plug in pi, finally, we have 2 times the sine of pi, which is 2 times 0. So we're back at the point 0, 0, or pi 0. Those are just different ways of saying the same point. So if you notice, we have these 4 points right here, and you may not be able to see it, but if you were to add in some extra points here, you would see that this makes a circle. So we have a circle going through these 4 points, and it has a radius of 1. So we have this distance right here. That's the center of the circle, the dot I'm drawing, and that is a radius of 1. Okay, so what this equation makes, r equals 2 sine of theta, this makes a circle of radius 1. But this time it's not centered at the origin, it's centered somewhere else. So if we wanted to find a rectangular equation for this, we could start with our general formula. So we have r squared is equal to x minus h squared plus y minus k squared. And so if we look at the center of our circle, in rectangular coordinates, this would be the coordinate 0, 1, because we are on the positive y-axis and we've gone up 1 unit. So h is going to be 0 and k is going to be 1. And our radius is 1, so that is all the substituting that we need to do for this. And so if we simplify, we just get that 1 is equal to x squared plus y minus 1 squared. Alright, so that is the rectangular equation for this circle. But if you notice, this rectangular equation is much more complicated than the other circle we did. And so this is one of those examples where this polar equation is much nicer, even though you may not be used to this yet. But down the road, it can be very useful. Alright, so now basically what we're going to do is just go through a few different types of polar equations. So we've already kind of looked at the circle, and the one that we just looked at was of this form. So we had some number times the sine of theta. And so what I've done here is I've just given you the equations, and then I've given you what the graphs of these kind of look like. So the first one, this is the r equals a times the cosine of theta, and this is r equals a times the sine of theta. So if you notice, these circles are they're either tangent to the x-axis or they're tangent to the y-axis. And all tangent means is that it intersects at one point. So these circles will always do this. And the diameter of the circle comes from that constant a that you're multiplying by either the sine or cosine. And so in the previous example, we had r was equal to 2 times the sine of theta. So what that equation tells us is that the diameter was equal to 2, which means the radius is equal to 1. So we actually didn't have to plug in all of those values to figure out what the radius was, but that gives you kind of an idea of where it comes from. All right. So that's probably the simplest ones to do. The rest of these get very complicated. So the next one we're going to look at is what's called a limacon. So this is a French word, as you can tell by the little curly Q on the C there. And these come in many different flavors. So they're always of the form some number plus or minus some number times either the cosine or the sine. And A and B both need to be positive. So we don't want any negative numbers in for A and B. However, you could have a negative sign pop up because we're allowing a plus or minus there. So the first type of limacon that you might see is one with an inner loop. So it looks like this weird kind of loop-de-loop shape that you see there. And we get this by taking the ratio of A to B. So all of these different kinds of limacons arise just from the ratio of A to B. And if A over B is less than 1, we know that it's going to have an inner loop. And the inner loop is just this little piece right here that looks like a loop on the inside. And the way we get the radius of that is we just take the absolute value of A minus the absolute value of B. Okay, so that's the first kind. The next kind is if A over B is equal to 1, and then we call it a cardioid. And so cardioid might make you think of a heart, and that's exactly why we call it this. Because if you kind of look at this and imagine a heart that's been kind of rounded on the side, it looks a bit like a heart. Maybe, I don't know. So that is a cardioid. Now, if A over B is between 1 and 2, then we call it dimpled. And that comes from this little area right here. So it's not a full-on point like the last one, so it's not doing this, but it still has a little bit of a curve to it like that. Okay, so that's a dimpled limacon. And finally, the last kind, if A over B is greater than 2, then we call it convex. And so you might think that this looks like a circle, but it's kind of flat right here, whereas a circle would be more curved. So it is a different graph, so don't just say it's a circle. It would be a convex limacon. All right? And for all of these graphs, we can get the maximum radius, which is the distance from this kind of flattened point over to the middle, or from this side to the middle, and all we have to do there is the absolute value of A plus the absolute value of B. So those are the limacon graphs. All right, next we have my favorite, the rose curves. I think they're a lot of people's favorite because they really do look like flowers. So all of these curves are going to be of the form some number times the cosine or sine of a multiple of theta. So it's important to note that that n goes with the theta, and we want to make sure that n is at least 2. So if you make sure that n is at least 2, that's whenever you get these flower shapes popping up. Now if n is an odd number, then we get exactly that many equally spaced petals. So if you look at the example of the picture here, we have n equal to 3, and so this should be the equation A times the cosine of 3 theta, or the sine, I'm not really sure, but this might be an example of it. So we don't really know what A is, but we do know that n has to be 3 because there are 3 petals in this graph. Okay? Now, if n is even, then we actually get double the petals. So the petal number will be 2n. So an example here is if n is equal to 4. So notice we don't really know if this is sine or cosine, but the important thing is that since n is equal to 4, we actually get 8 petals if you look around that graph. And again, here we have a maximum radius. So in the case of this graph, the maximum radius is going to be from the center out to the end of a petal. All right, and that will simply be the number A. So that number A tells you how big these flower petals are, and the number N tells you how many flower petals you have. All right, the third type of graph we're going to look at is what's called a lemniscate. And so this is sort of related to the rose curves, but a little bit different. So in this case, we actually have an r squared on the left side, and we get an a squared on the right side. And these will always have a multiple of 2 theta as well. So what we get are these little figure 8 shapes that are rotated a little bit from the horizontal or the vertical. Okay, but they do kind of look like the rose curves a little bit. And again, we have a maximum radius of A. So just like with the rose curves, this maximum radius goes from the center of the graph all the way to that petal. All right. So again, it's kind of telling you how big the petals are. Okay, so those are your basic kinds of polar graphs, and I know it's a lot of information, but it's one of those things that you kind of just have to practice and get used to. But one thing we can do with these polar graphs is test them for different kinds of symmetry. So if you remember back in Algebra 170, 113, you probably learned about even and odd graphs, and I know we did a little bit of that with the trig functions. Polar graphs are the same way. They can have horizontal symmetry, they can have 180-degree symmetry, or they can have vertical symmetry. So the names of these different symmetries are a little different though. We don't usually call them even and odd because we're not talking about an x and a y axis. So a graph may have symmetry with respect to the polar axis, which if you remember, the polar axis was what we call the horizontal axis, so that is why it's horizontal symmetry. We could also have symmetry with respect to the pole, and remember the pole is the origin in the polar coordinate system, so that means that we have 180-degree rotational symmetry about the origin. And finally, we could have the line theta is equal to pi over 2, and so that would be the same as the vertical axis in the polar coordinate system. So we can test for these algebraically just like we did back in algebra. So if a polar equation is unchanged when we replace, so basically if you remember from algebra, you change x to negative x and you kind of play around with the algebra a little bit. And if you get certain things to happen, then it tells you whether it's even, odd, or neither. Well, this is the same thing, except we're going to replace the different letters by either negative theta, negative r, things like that. So first, if we replace theta by negative theta, and the equation remains unchanged, then the graph is symmetric about the polar axis. So that's how we get that horizontal symmetry. If we replace r by negative r, then the graph is symmetric about the pole. So that's how we get that 180-degree origin symmetry. And finally, if we replace theta by pi minus theta, then the graph is symmetric about the line theta equal to pi over 2. And remember that in either of those three cases, for the symmetry to occur, the equation has to be unchanged when we make those substitutions. So now we'll look at a few examples of this. So what I've done first is just given you a picture of each type of symmetry, so you kind of have some examples there. So the first one, we have symmetry about the polar axis. So notice if we were to fold this graph over the polar axis, then it would match up on both sides. Symmetry about the pole. So imagine taking your paper and turning this graph all the way around, upside down, and what you'd notice is that the graph stays the same. And so that is symmetry about the pole. And finally, for symmetry about the line theta equals pi over 2, imagine taking that vertical axis as the folding line, and your graph matches up on itself if you fold over that vertical line. So those are the three kinds of symmetry. So now I'm going to show you how to do that algebraically. So we're going to take as our example the function r is equal to 3 plus 2 times cosine of theta. So just for some practice, let's think about what this graph looks like. So because we have 3 plus 2 times the cosine of theta, we know that this is a limicon, because we have something plus something times either cosine or sine. So it's a limicon, and if we take the ratio of a to b, so if we take a over b, that's equal to 3 over 2, which is 1.5, and 1.5 is in between 1 and 2. So what this tells us is that we have a dimpled limicon. So if you were to graph this in a calculator or by hand, you would see that it looks like a circle with a little bump in it. Alright, so now let's see what kind of symmetry this has. So because you already know this, you might know that it has some kind of symmetry, and I think it will. So let's see. So for the first one, we're going to take the equation, and we're going to plug in negative theta for theta. So we'll get r is equal to 3 plus 2 times the cosine of negative theta. Now, if you remember, cosine is an even function. So if we plug a negative number into cosine, it kind of just goes away. Okay? So what we get is that this is just equal to 3 plus 2 times the cosine of theta. And because this equation here matches our original equation, we can say that the graph has symmetry about the polar axis. Alright, so it has symmetry about the polar axis, and if you think about what that dimpled limicon looks like, it looks like that, which kind of makes sense. You can kind of think about it that way. So let's try another type. So next, we're going to plug in negative r for r. So we get negative r is equal to 3 plus 2 times the cosine of theta. So now let's get r by itself. So we divide by the negative 1, and we get r is equal to negative 3 minus 2 times the cosine of theta. So this equation is not the same as the original equation, so we would say no symmetry about the pole. And if you think about what that dimpled limicon looks like, that makes sense, because if we turn this paper 180 degrees, we would end up with the dimple on this side instead of the other side, and so you can kind of see how that wouldn't work. So finally, let's check for that vertical symmetry, which you can probably already guess is not going to work, but we're going to run through it anyway. So finally, we're going to take our equation, and for theta, we're going to substitute in pi minus theta. So we get 3 plus 2 times the cosine of pi minus theta. So let's think about what this does. So if we have a difference inside of a cosine, we can expand that using our sum and difference formulas back from lesson 5, I think it was. Yeah, so what we get is 3 plus 2 times the cosine of pi times the cosine of theta plus the sine of theta, the sine of pi times the sine of theta. All right. And if we think about what the cosine and sine of pi are, we get 3 plus 2 times negative 1 times the cosine of theta plus 0 times the sine of theta. So if we do a little bit of algebra, this term goes away, and what we're left with is 3 minus 2 times the cosine of theta. And so what we've arrived at is an equation that looks really similar to our original, but it's still not quite the same. We have a negative here instead of a positive, so it's not the same equation, and we can say that this is not symmetric about the line theta is equal to pi over 2. So that is how you test for the 3 different kinds of symmetry in a polar equation. Now, this isn't quite as straightforward as with your regular rectangular equations, because even if all of these algebraic tests fail, a graph could actually still have symmetry. And one example of this is the spiral of Archimedes. And so this graph looks like the following. It's a pretty cool looking graph, I think. But if you were to perform all of those algebraic tests for symmetry, they would all fail. But you can clearly see from the graph that the graph does have a vertical symmetry to it. So this might be an interesting test question down the road for some theoretical question at the beginning of your test. So keep that in mind. So now we're going to go and graph some polar equations. And so I've just put some steps in here for you to, as you're getting started, just to help you remember what to do. So the first thing you always want to do is figure out what graph you're talking about. Okay, and the way you do that is look at the equation and match it to one of the forms of the equations we just went over in the earlier in this video. Then you want to find the value of the maximum radius and what angle it goes with. So basically you want to find that furthest point out on the graph, and so you want to let r equal that maximum radius and figure out what point you get. Then you want to find the zeros of r. So this isn't zeros in the sense of how you normally think of zeros as x-intercepts. What we mean here is find the angles that have a radius of 0. So let r equal 0 and then figure out the angles. And what this will tell you is where does the graph start to repeat on itself, or where does it cross that origin. Alright, and then finally, oh, well, there's the r equal to 0. Okay, so we talked about that. And then finally, you just want to fill in the graph shape with more points. So just like we did before with a table of values, that's a very nice way to do it. You can also test for symmetry. That helps as well, just to make sure that your graph looks right. So those are some good ways to help you graph a polar equation. And just a note on the domain, we kind of already talked about this, but when the same value of r is obtained at a theta and at theta plus 2k pi. So whenever you start adding the 2 pi to your angles, that's when you start repeating your r's. And so what happens is the graph just keeps looping on itself, and that's how you know that you need to stop. Because if you just keep plugging in thetas, you're just going to keep getting the same points you already got. Alright, so let's practice by graphing r is equal to 1 minus 2 times the cosine of theta. So right off the bat, if you notice the form of the equation, we can say that this is a limison. Okay, but then we need to figure out what kind of limison this is. So we need to check the ratio a over b. And in this case, we get 1 over 2, which is less than 1. So because this is less than 1, we know that it has an inner loop. So this will be an inner loop limison, so it's going to look something like that. All right? And we can figure out the radius of the inner loop by simply doing the absolute value of a, so the absolute value of 1, minus the absolute value of 2. And so what we get is 1 minus 2, which is negative 1. So what this tells us is that our radius is going to be on this side of the graph. So it's going to be like this rather than on this side. like in the example before. So we're going to have an inner loop where we have a point here, and that's the inner loop of my limison. So now what we can do is just go through and find some more values. Well, I guess we could find the maximum radius if we wanted. Let's go ahead and do that. So the max radius, we do the absolute value of 1 plus the absolute value of 2, and that's going to give us 1 plus 2, which is 3. And so we know that this will occur this way, and so we get, oh sorry, not right there. Alright, so that would be our maximum radius. So again, the maximum radius is just from the center out to the edge. So we won't have any points past that point. We won't have anything over here, and we also won't have anything over here. Okay, so now let's make a table of values and fill in the missing points. So we have R and theta columns, and actually let me switch those because we're going to be solving for R. So we have theta, we have R. So let's pick theta to be our multiples of pi over 2. So we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if we plug these in for theta, we get that 1 minus 2 times the cosine of 0, which gives us 1 minus 2 times 1, which is negative 1. If we plug in pi over 2, we get 1 minus 2 times the cosine of pi over 2, which is 1 minus 2 times 0, which just gives us 1. So we know that this point, we go out to the circle of radius 1 and around to pi over 2. For pi, we already got the point at pi, but we'll solve it anyway. So we got 1 minus 2 times the cosine of pi, which is 1 minus 2 times negative 1, which gives us 3. And so that indeed matches up with what we thought with our max radius. Now we have 1 minus 2 times the cosine of 3 pi over 2, which is 1 minus 2 times 0 again, which is 1. So this time we go out to the circle of radius 1 and around to 3 pi over 2. And finally we have 2 pi, but that's just going to keep repeating on the point of 0. So we'll just stop there. And the way that we finish out this graph is we just connect all of our dots with as smooth of a curve as you can get. Alright, so let's look at another example where we have R equal to 2 times the cosine of 2 theta. So if we look at the form of this equation, we know that we're going to get a rose curve. Alright, and we know that the number of petals is going to be 2 times 2 because the 2 next to the theta is an even number, and so we know that we'll have twice as many petals, so we'll have 4 petals. Now the 2 next to the cosine we know is going to be the radius of the petal, so the max radius is going to be 2. So each of these petals from the center to the edge of the petal will have a distance of 2. So that's a good place to get started. And from here, let's just make a table of values. So we have theta, we have R. Let's pick our thetas to just be our multiples of pi over 2 again. So we have 0, pi over 2, pi, 3 pi over 2. And so let's figure out what our radiuses are. So we have 2 times the cosine of 2 times 0, which is 2 times the cosine of 0, which is 2 times 1, which is 2. Alright, so we know we have the point 2 comma 0. So let's see, we go out to the circle of radius 2 and we don't rotate at all. Next we have 2 times the cosine of 2 times pi over 2, which is 2 times the cosine of pi, which is negative 2, because the cosine of pi is negative 1. So we go out to the circle of radius 2 in the negative direction, and we go around pi over 2. So then for the point where theta is equal to pi, we have 2 times the cosine of 2 times pi, which is 2 times 1, which is 2. So we go out to the circle of radius 2 and around an angle of pi. And then finally, we have 2 times the cosine of 2 times 3 pi over 2, which is 2 times the cosine of 3 pi, which is 2 times negative 1, which is negative 2. So we go to the circle of radius 2, but in the negative direction, and we go around 3 pi over 2 up to the top there. So while this might look like a circle, this is why we said first that it's a rose curve. So you know that for each of these maximum radii, or maximum radiuses, we must have a point in the middle, and all of our little flower petals must stem out from this point. So what we get are those 4 evenly spaced petals, one on each axis, and so that is your rose curve. All right? So hopefully graphing polar equations made a little bit of sense. I know that it's a lot to go over in one lesson, but just start working on the homework right here. And if you have any questions, please let me know.